Okay, I will talk a little bit about my company and what we did so far. So we, for example, formally verified the Ethereum deposit contract. So when Ethereum did the change from proof of work to proof of stake, there's a special contract, the deposit contract, where stakers can come in and deposit 32 ETH. That was one of our formal verification engagements. Then we formally verified Uniswap, Optimism, Lido, parts of EigenLayer. So, and as you might notice, all these are like pretty high-profile clients, but eventually, well, formal methods needs to become way more accessible so that not just like the top tiers in the space can afford it and can do it. So now, for the last 2 years, we were basically focusing on making our tools that we've been using in these engagements to make them more accessible to everyone so that, well, independent security researchers and also like developer teams can run their own formal methods. And most of our tools are actually completely open source, so it's been possible for a long time to do that. But the problem was that the developer experience was just not there yet. And that's where we now try to improve on. And in this session, I will present you two different approaches that we took, which I think are pretty innovative in this space. All right, thank you very much. So, as I said, two new perspectives on formal verification. The first one is like going from debugging, and I think every developer knows in this room knows what a debugger is. And a debugger is pretty easy to use, right? And we developed a new tool that is a symbolic execution debugger. So if you are already familiar with how to debug your code, it just becomes a smaller step towards understanding symbolic execution. The other approach is testing. You probably heard of it. You're all doing it. You're using unit tests. You're properly writing property tests or fuzzing. If not, you should be. And property tests are also a great way of a first step to become a formal methods expert by just turning your property tests into symbolic tests. And I will show you later how this actually works. So debugging. Just 1 week ago, we released our Solidity debugger. I think it's needed, especially since Truffle shut down and their debugger is not continued anymore. There's basically no maintained debugger that opts into Visual Studio Code. So we're trying to close this gap. This debugger is not perfect yet. At runtime verification, we like to build our tools in public. So we really release them in an imperfect state, and then we depend on the community to provide feedback and prioritize the features. For example, one missing feature of this debugger is you can inspect the EVM state, you can inspect the call data, the stack, and the memory, and the storage. But to be actually useful, we need a way to show Solidity variables instead of the low-level details of the EVM. And that's a planned feature. The Ethereum Foundation is very helpful. They are developing a new debugging format that will make it possible actually for us to reliably decode variables. It's just, at the moment, the Solidity compiler doesn't give us sufficient information to do it. So we are kind of dependent on the Ethereum Foundation to push this debug format. The debugger is now on the Visual Studio Code marketplace. It's it's a beta version, so you actually need to have an API key that you get from our website. But the goal is to open source it. So it's actually 90% open source, but there are some components that are not open sourced yet, but they will be over the next weeks or months, depending on how fast these features stabilize. Okay, let's go into symbolic debugging. And we have a demo for that, so that's one of the advanced features of this debugger. So you can actually go to try.symbolic.runtimeverification.com, and without installing anything, it just loads a Visual Studio Code instance in your browser. It's a very limited demo. It has the wrapped ETH contract in it, and you can just see how symbolic execution unfolds before your eyes. So what is symbolic execution, actually? It's array of systematically exploring the entire state space of your smart contracts. So instead of running your program from a concrete initial state, you make your initial state symbolic. And by that means, what that means is just you introduce some variables during the execution. So you all know variables from Solidity. They only exist like at the source code level. But when you're actually running the program, these variables disappear. So and now we introduce symbolic variables, which are variables that exist during the runtime of your program. And you're actually a very good mental symbolic executor. So whenever you read code, you are basically doing it symbolically in your head. You're not running, like if you're reading this piece of code, you're not executing it on concrete values, but you just make some assumptions about the values. And then you process all the branches basically, and then you have a mental model that of this control flow graph, right? When you look at this code, you see, okay, there's an if statement. What happens if I go inside the then branch? You know that the if condition must be satisfied. So you record a path condition here, then you just revert, and then you also know, okay, you also need to look at the else branch. So and you do all this in in milliseconds in your head, right? It's very fast process. So, and while I was doing audits at runtime verification, I was drawing these diagrams a lot on just pen and paper because I found them so useful. I'm a very visual person. So wouldn't it be nice if we could just generate these control flow graphs for you in a very visual way? And that is actually what the symbolic execution mode can do. So if you're now symbolically debugging a program, you can actually, you start at the FizzBuzz function, so you start at the first line here in line 18, then you have this if statement, and you can see the branches actually. They are visualized for you. And you can see that the debugger here actually has 2 cursors, so that means there are currently 2 active branches that are being explored. A really cool feature, a really cool side effect of this feature is, time travel debugging. So instead of just stepping to the next line in the code, you can go backwards, which is really cool because usually you you run into an error condition and then you want to go backwards to find the source of this error condition. And one of the cool features with this graph is that it's basically like time traveling debugging on steroids. So you can not just go one step back, but you can jump to any point in execution of your smart contract. And you can even, if we expand on this timeline metaphor, you can even jump to alternative timelines. And by that, I mean alternative execution branches of your smart contract. So whenever, this is a branch, by the way, so we have an if statement, we go into the then branch or into the else branch. And you can just, directly by clicking on these boxes, you can directly jump to this part of the code. I know I have a very technical audience in front of me. So you probably all know, well, Ethereum is like a state transition system. You have states, that is all the storage and all the accounts and all the balances. And then you have transactions, and transactions are the state transitions. They change the state every time a transaction is applied. Let's look at the EVM, at the Ethereum network. What happened in 2015? We mined the Genesis block. This was our initial state, and we did a bunch of transactions. And some of these transactions were actually exploits, exploiting an inconsistent state on the blockchain, basically. And now we are here, and if we look at the past has been a linear history, right? All the transactions get sequenced linearly. So now we want to avoid these cases, but doing this at the present is way harder. Even detecting these bugs in the past is sometimes hard, and analyzing the hacks and what's going on, it can be really tricky. But for the future, securing our smart contracts to avoid bugs is even more difficult because, well, we cannot predict the future, right? We can look at the past, it's all linear, but for the future, there's an infinite amount of possibilities for the next transaction and the next to the next transaction. So if you're testing your smart contracts, you're basically following one or two of these paths. Maybe you're following, like if you're using fuzzing, you're following like 1 million of these paths even. But still, like if you don't hit this path that's triggering the bug, well, then you could be hacked, right? So it's sufficient if there's just one stage, just one possibility to trigger a bug in your code base to drain your smart contracts. So that's what we try to avoid. I'm not sure if I want to make this example. Do I have a timer, by the way, or can anybody tell me what's the time? 10 minutes in? 8 minutes in. Okay, then I will do it. Okay, let's take a look at a transfer function. So now we are fixing our view on just a single transfer function of some, I don't know, ERC20 token. You can call the transfer function with many different parameter combinations. You can transfer 10 tokens from Alice to Bob, 20 tokens from Alice to Bob, 30 tokens from Alice to Alice. And there's an infinite amount of possibilities that you can take. And every time you do that with a different parameter combination, you will end up in a different successor state. And maybe there's one of these successor states that's buggy and that could be exploited. So how can we make sure that we actually find the correct parameter combination that triggers the bug? So what we do at runtime verification, and that is like a more general concept that's called symbolic execution, instead of starting from a very concrete initial state, where Alice has a balance of 100 and Bob has a balance of 0, we actually don't make assumptions about Alice and Bob and who they are and how much balances they have. We just say, hey, okay, let's assume the sending address is just a variable and it has a balance of X, and the receiving address is also just some variable that has a balance of Y. Then we execute this transfer from function from a generic address to another generic address with some arbitrary amount of value. And now the cool thing is that when we do it in this way, we actually just have 2 successor states for most reasonable implementations of ERC transfer functions. So there's one successor state when the from and the to address are actually different. So you see that the from address is discounted this value, and the to address receives some value. And then there's the other case, the other branch, where the from and the to address are actually the same, so the balances don't change. So that basically makes it possible for us to collapse this ever unfolding state space from like an infinite amount of possibilities into just one single abstract transaction that we need to debug. So that's pretty strong. Yeah, that's pretty strong. That's all I got to say today about debugging. I suggest you all try it out and send me your feedback. As I said, it's just this symbolic debugger has just been released last week, so there's probably expect some bugs maybe. But if there's a feature that you're missing, if it's not the Solidity debugger that you want to have, then let us know, because we are very flexible and we like to get your opinion on it. All right, so let's talk about the other perspective. So this was, the first part was, okay, how can we go from classical debugging to symbolic debugging? And I think it's a very visual model to, I think it's the first visual model actually that helps you visualize how symbolic execution works. Like if you're reading papers on symbolic execution or formal methods, they are usually very math heavy. And math can be very tricky to visualize. Of course, there are branches like geometry where that is easy. But I think with this debugger, we found a very good visual metaphor to visualize symbolic execution also. So let's talk about testing. And again, I assume that you're all technical, you're all doing tests. So just a quick reminder, so we have unit tests, and what a unit test does is it tests a function on a fixed parameter combination. And what a fuzzing or property test does, it tests a function on random parameter combinations. And that is a bit a simplification. I know Jocelyn will correct me on that. So fuzzing is actually more clever. They are not just using random values, but they are using clever heuristics like constant mining, so they look at the constants that are defined in your smart contracts and prefer them to use it as an input. But it's basically sampling some input space for you. And that's way better than just doing unit testing. So, and you should do both. Like start with a unit test, then generalize it maybe into a property test. And now symbolic testing is the practice of testing a function on all possible input combinations. And obviously, we have to be very clever on how to do that. We cannot just sample all the parameter combinations. If you just have a function with one uint 256 data type, and you want to test it on all possible inputs, that would take you more time that we have left in this universe. And if you think you could be smart and just parallelize it, well, bad news is you would, like, just to build the hardware to run it on parallel, you would need more atoms that we have in the universe. So uint 256 is really, 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 really huge. And that's just one parameter. Now, if you have like a function with 2 or 3 parameters, the state space basically explodes and it becomes even more difficult. So obviously, when we say symbolic testing, and I say we test all the inputs, we do it in a different way. We just do not sample all the parameter combinations, but we do this is symbolic execution stuff that I showed before. So I'm basically saying symbolic testing is a way of increasing the confidence in your test suite. So just as property testing is increasing the confidence over unit testing, symbolic testing is increasing the confidence in your tests for property tests. So here's another example. So if we look at a fuzzer, how does it work? You have your smart contract, and then you have a specification or a test suite, and I'm using these terms here interchangeably. And sometimes formal verification engineers like to make a distinction here, but I will tell you in a minute why we don't make this distinction at runtime verification and why this is actually beneficial. So you have smart contracts, you have a test suite, you run your fuzzer on it, and maybe you're lucky and you find a counterexample, and that's great actually. It's not bad, because then you know you have a bug in your smart contracts and you need to fix it, and then you can run it again. That's super cool. So, and eventually your fuzzer says, hey, your test passed. And test passed is actually, it's a little bit, how do you interpret this result? Like, it does not say there are no counterexamples, there are no bugs. But what does it say is really, I don't know. So it's saying, I'm actually not sure if there is a counterexample, if there's a case that we probably missed. And that is because it's using this the sampling of inputs, but it could just be that it missed the one parameter combination that would trigger the bug. So it's actually not, it's saying not sure. So now what is symbolic testing? Instead of a fuzzer in the middle, you have a prover. You still have just a smart contract and the specification, so all things stay the same. But your outputs are a little bit different. So there's an additional output. So you, in the lucky case, the prover finds some counterexample, and that's again very good. So you know you need to go back to your smart contract, run it again, and hope that the counterexample disappears. It can also be the case that a prover just surrenders and tells, hey, I'm not sure, I don't know if there's a parameter combinations that make your test fail. I'm stuck at this point. And what you do in formal methods then, or in formal verification, is you need to help the prover. You need to provide it a custom lemma. So because this is basically, this is like a math professor, an automated math professor. And sometimes you need to just to give it a lemma so that it can make progress. And I think that's one of the cool things that sets our tooling apart from other formal verification frameworks, is that whenever you are in a stuck state, you can actually help the prover by writing a custom lemma and help it make progress. So what I'm saying is, proving is not as automated as testing, but it's really an interactive. It's an interactive process with the with the prover, the engineers that does the proving, and the automated prover, the machine that helps you do this. But we have this third input, and this is really cool. If you repeat this cycle, like you have a counterexample, fix the code, you'll get stuck, help the prover. Then eventually you can reach a proof of correctness. And this proof of correctness really tells you, hey, we have a solid, rigorous mathematical proof that no parameter combination can exist that would make your test fail. And these proofs are really, they are super rigorous. They are way more rigorous than the proofs that you did in university by pen and paper. They are machine checkable, so they can give you pretty strong correctness guarantees. So formal verification engineers, they like to call their test suites specifications. At runtime verification, we think, well, test suite. If you ask a developer basically to write a specification for their code, they don't know what to do. So how do you what do you mean by specification? How do you do that? And usually how this works is you start by drafting a natural language specification that just describes in plain English what your smart contract is supposed to do and what it's not supposed to do. And then you have, classically, you then have a formal verification engineer who talks to the developer team to turn this natural language specification into a formal language. So because, well, natural plain English is, there's room for interpretation. Sometimes the same sentence can be interpreted differently by two different persons. So we actually need to find a way to make it more formal and remove any ambiguities in the language. So we turn it into a formal specification. And classically, these formal specification languages, they are very weird. And they are very, they are mostly coming from some research projects. They are very math intense. They don't look like programming languages at all. But what we're doing in runtime verification now is we say, hey, what if you could just write your specification in Solidity itself? Because that's the language of the developer teams. So now if you ask a developer to provide a test suite for you, then they will know what to do. Like if you ask them specification, no idea. Test suite, okay, I can do that. So, and our tool control is essentially doing exactly this. So it's using it's reusing property tests in the style of Foundry, and symbolically executes your tests to explore all the possible states. So control is really, it's the combination of Foundry tests with KEVM, which is formal verification. And it gives you a really nice, it makes it easier for you to draft specifications, and also it eliminates kind of misunderstandings between the formal verification teams and the developer teams, because now it becomes more clear to everyone what the specification is actually supposed to do. It's a command line tool, so the commands are pretty simple. You just run control build to compile your smart contracts, control proof, and give it a contract name and a test name to run the test. And then, well, it will either say test passed, and that actually means you have found this proof, or more likely it will say, I'm stuck, I don't know what to do. And then you have these helper functions here, control show and control view KCFG, and these are just two methods of inspecting the state where your prover got stuck. And then you need to inspect the state, and you need to write a lemma to help the prover get over the stuck state. This can be very challenging, I want to be honest. So this is not easy at the moment. The problem here is when you need to write these lemmas, actually, we haven't found a way yet to express these lemmas in Solidity itself. So you actually have to fall back to a formal language, so to this specification stuff. And these formal languages, they are pretty hard to read for somebody who's not a PhD in formal methods. So this process can be actually very difficult, not going to lie here. But we are experimenting with some features, and actually we want to find a way to express these lemmas in Solidity itself, so that this process will also become more native to a Solidity developer. Control list just lists you all the existing proofs that you have been executed, that have executed so far. Some of them passed, some of them failed. And the cool thing about control is, as I said, it's open source, and you can run it on your own CI pipeline. And this is really important because, well, the other downside of formal methods is that they are super compute intensive. So running a fuzzer is extremely fast. It can give you super fast results. And that allows you to iterate really fast on your code, on your tests. Formal methods, on the other side, is very slower, very more compute intensive. So, and just to give you some examples, depending on the code size, at runtime verification, we see proving times that range from some minutes to some hours, and in some extreme cases, it can even take some days just to find the proof. So you actually don't want to, and if you have a proof that takes some hours, you actually don't want to run it on your own computer, because you won't be able to do anything else on your computer in this time, because it's using 99% of your CPU power. But what you can do is you can just enable control on your CI pipeline, and then it runs maybe on your GitHub runner overnight or on every pull request that you merge into the master branch. And it keeps making sure that all the proofs that you have are still passing. And sometimes it will find a counterexample. So some other, I would just want to highlight some specifics of control that maybe sets it apart from some other formal methods tools. So first of all, as I said, control is fully open source. You can run it on your own CI pipeline. That's really strong. It's also reasonably, arguably, the most expressive formal verification framework that we have. So it's based on a logic that's called matching logic. And as far as I know, there's only two tools currently, two formal method tools for Solidity and Ethereum that can reason about loops. So why are loops so difficult? Well, I explained this branching structure, right, for an if statement. Now, if you have a loop, what you basically need to do is you need to branch off like an incredible amount of time. So you assume, okay, you consider the case, okay, what happens if my loop terminates without a single iteration? What happens if my loop terminates after one iteration, after two iterations, after three iterations? So you have a lot of branching. And what most provers do is at some point they just give up. So as a formal verification engineer, you can say, okay, I want that my loops are executed up until 3 or 4 or 5 times, and then after that, just give up. And that's not a really cool way to do things, because, well, you lose lots of the strong correctness guarantees, and then in many cases, you will be better off just using a fuzzer if you have loops in your code than using formal methods. So you can actually, sometimes you can get stronger correctness guarantees by using a fuzzer than by using a formal methods tools, and that's strange. So at runtime verification, we have the ability to reason about loops, and that works through something that we call loop invariance. So you actually compute, what we are doing is we kind of compute a closed formula that captures the effect of your loop. It's very difficult, very difficult thing actually to do, but we are doing it. So it's possible, but it's time consuming. Not going to lie here. And if you think, well, loops, I don't have so many loops in my Solidity program, that shouldn't be a problem, then you're wrong, because we are talking about bytecode level loops here and not Solidity loops. And the Solidity compiler sometimes generates loops on the bytecode level that you wouldn't see on the Solidity source code level. So basically, whenever you have some dynamic data, like strings, bytes, dynamic arrays, mappings, when you have this dynamic data, not mappings, sorry, but arrays, strings, bytes, when you're passing around these parameters, then the Solidity compiler will generate a loop somewhere to copy your data from one data location to another. Also, our approach, our tool control does not make any simplifying assumptions about the EVM. Lots of tools are doing that, but EVM is actually, or control is actually built on a complete formal semantics of EVM, which is called KEVM. It's inspectable. Also, that's some killer feature that not many provers have. So in many cases, when your prover gets into the stuck state, it gives you very little information on how you would proceed. But our prover makes like every single piece of the EVM configuration at the point where it's stuck inspectable. And not just at the point where it's stuck. Basically, you can see the entire execution trace and you get full information. And it's semi-automated. That means, well, we try to favor automation over just this interactive process, but at least we have the possibility for a formal verification engineer to step in and guide the prover to make more progress. Also, this nice GitHub project, ETH SC comp benchmarks, that is basically a repository that benchmarks different formal verification tools that exist for Solidity and EVM. And the results are really interesting. So if you look at the results, you will see that control is actually the best in class when it comes to how many instances can we solve. That means how many proofs can we find automatically. And we just, like, at the beginning of the year, it was still HEVM, and now we just passed them. But of course, like all this stuff, expositivity, precision, inspection, interactive proving comes at a cost. And that cost for control is compute power. So our approach is usually performing slower than all the other approaches that exist. All right, that's all I've got for today. If you're interested in our tools, so the first one, debugger, is called Symbolic. The second one, testing, is control. We are currently working on making these tools more interconnected so that you can actually use Symbolic to debug your control tests. So basically, Symbolic becomes a cool user interface for using control. Yeah, if you like this, if you like the stuff, if you want to try our tools, make sure to check them out. Follow us on Twitter or on Discord. If you have some feedback, again, just share it with us so we can improve on our tooling. And yeah, well, be honest with us. Like, we can only improve if you give us very honest feedback. Okay, thank you very much.